In question 1a, you were asked about assumptions to be made in modelling this disease. Occurrences of the disease are independent, and the probability of catching the disease remains constant. In part B, we can assume that we've got a binomial distribution, and we want to find the probability of 2 people having the disease. So the probability that x is exactly equal to 2, where x is the number of people with the disease, probability x equals 2 is 10c to 0.03 to the power 2 and 0.97 to the power 8, and that works out to be 0.0317. In part C, to work out the mean, so that's n times p. We've got 100 people now, so it's 100 times 0.03, which is 3, and then the variance is np1 minus p, so that's 100 times 0.03 times 0.97, which works out to be 2.91. In part D, we can use a Poisson approximation, and the parameter is 3. 2.91 is close to 3. So we're after the probability that y is greater than 5. So it says if more than 5, so that's greater than 5, so that's 1 minus the probability that y is less than or equal to 5. So using the tables, that works out to be 0.0839. And in part E, the conditions would be that there's a large sample size, and a small probability of success. Okay. Now in question 2 of the stats paper here, we can say that x belongs to the binomial distribution with parameters 100 and 0.58, and x is the number of females. So therefore we can approximate by saying y is a normal distribution, and the numbers work out to be 58 and 24.36. Why is that? That's because the mean is 100 times 0.58, which is 58, and the variance is 100 times 0.58 times 0.42, which works out to be 24.36. So we're after the probability that more than half, so we want to find the probability that y is greater than 50, which is the same as saying y is greater than or equal to 51, which is 1 minus the probability that y is less than or equal to 50. But if we draw the normal distribution, there's 58, there's 50, we want it to be less than or equal to 50. So if this is 50 here, then we need to include that area there. So what we'll need to do is to make z has to be less than or equal to 50.5 minus 58 over root 24.36. Now that works out to be minus 1.52. So let's go on to the next slide. So what we're after is this area here. that's the same as this area here. So it's 1 minus the probability that z is greater than 1.52. But in the tables we do less than, so that's simply less than 1.52. So the tables will give us this area here. And that works out to be 0.9357. So just in case it's not clear, we were after 1 minus this probability here. We wanted 1 minus this probability here. So we were after this whole area here. And that whole area there is this area here that I've shaded in red. Now in question 3 we're given the cumulative probability. So it must be true that f of 5 equals 1, because f of 5 is the probability that x is less than or equal to 5, and these numbers here say that when x is greater than 5 it's 1. This works from 2 up to 5, so f of 5 must be 1. So if I put 5 into there, it's k 95 minus 25 minus 34 equals 1. So therefore k is 1 over 36. In part B we want the probability that x is greater than 4. So that's 1 minus the probability that x is less than or equal to 4. So if I put 4 into this expression here, so it's 1 minus 1/36 of 19 times 4 minus 4 squared minus 34. So that's 1 minus 26 over 36, which is 10 over 36, or 5 over 18. And finally, in part C, we will need to find the probability density function, and that you get by differentiating the cumulative. So if you differentiate k 19x minus x squared minus 34, you get this. So the whole lot works out to be, so f of x is 1/36 of 19 minus 2x when x is between 2 and 5, and otherwise in any other place it's 0.